A star in the Milky Way behaves so much like a black hole that scientists cannot tell the difference without extreme instruments. It is not a black hole, it is not even a neutron star, it is something else, and it might be the most extreme survivor the universe has ever produced. The object is catalogued as PSR J0952+0607. It sits in the constellation Sextans, roughly 4,100 light-years from Earth. It was first identified in 2017 as a millisecond pulsar, a rapidly rotating neutron star, spinning at approximately 707 rotations per second, near the theoretical maximum rate at which a neutron star can rotate before its own surface centripetal forces tear it apart. In 2022, and updated through 2024, a team led by Roger Romani at Stanford University used data from the NICER X-ray telescope aboard the International Space Station to measure its mass. The result, published in the Astrophysical Journal Letters, placed PSR J0952+0607 at approximately 2.35 solar masses. The previous record for a confirmed neutron star was around 2.1 solar masses. The difference is not small. It is the difference between a star that barely survives as a neutron star and a star that should have collapsed into a black hole. The current theoretical upper mass limit for a neutron star, the Tolman-Oppenheimer-Volkoff limit, is approximately 2.17 solar masses, though some exotic equations of state push this higher. At 2.35 solar masses, PSR J0952+0607 is sitting in territory where most astrophysical models predict black hole formation. It is the heaviest known neutron star candidate in existence. Why does it look like a black hole? Because its behavior blurs the line. A neutron star this massive has a Schwarzschild radius, the radius at which it would become a black hole, that is not far from its actual physical radius. Its surface gravity is approaching black hole levels. Its accretion environment, if it were actively feeding, would produce X-ray signatures nearly indistinguishable from low-mass black hole candidates. If you looked at it through a low-resolution telescope, you could easily mistake its X-ray flicker patterns for those of a small black hole. But it is not a black hole. It is a neutron star. The distinction matters because it tells us something profound about the physics of matter at the densest states achievable in the universe. A 2.35 solar mass neutron star means the equation of state for nuclear matter, the description of how the ultra-dense protons and neutrons inside the star interact, is much stiffer than most models predicted. The matter is more incompressible than expected, holding the star up against gravity at a mass that should have triggered total collapse. This is where a key piece of evidence comes in. PSR J0952+0607 is part of a binary system. The companion star is a cool, dim, very low-mass white dwarf. The system formed when a massive star and a lower-mass star evolved together, exchanged material, and the more massive star collapsed into a neutron star. The neutron star then spun up, the same way all millisecond pulsars do, by accreting material from its companion. Over billions of years, the neutron star gobbled enough matter from the companion to reach this extreme mass. In a 2022 study, Romani and collaborators compared the system to similar binary pulsars. They concluded that PSR J0952+0607 likely achieved its extreme mass through a particularly efficient accretion process, possibly because the companion star was very low mass and entirely consumed, leaving the neutron star with nowhere to shed its accumulated mass. What does it actually look like? A neutron star of this mass is roughly 12 to 13 kilometers in diameter. Its surface temperature has cooled over billions of years to perhaps 1 million Kelvin, still extremely hot by any human standard, but dim optically. It emits most of its energy in X-rays and gamma rays, particularly from its magnetic poles, where the pulsar mechanism accelerates charged particles to relativistic speeds and produces a focused beam of electromagnetic radiation. As it rotates 707 times per second, those beams sweep through space, and when one crosses our line of sight, we detect the rhythmic pulses that give pulsars their name. The challenge for the future is that finding an even heavier neutron star would push the equation of state toward the limits of what is physically possible. If a confirmed neutron star above roughly 2.5 solar masses is ever found, it would require exotic forms of matter inside the core, possibly strange quark matter, deconfined quark matter, or other states predicted by quantum chromodynamics, to hold it up against gravity. The door is not closed. Strange quark stars have been theorized for decades. They would be denser than ordinary neutron stars and could potentially be stable at higher masses. For now, PSR J0952+0607 stands as the boundary object, a star so massive it has become the most precise natural laboratory for nuclear physics we have ever found. So what do you think? Is this the heaviest neutron star we will ever find? Or is the universe hiding something even more extreme? Drop your answer below and follow for the cosmic extremes they never teach you in school.